Okay, guys. Some of your assignment is based upon what we call empirical formulas, and so I'll put one problem up here that you can at least see. Sometimes they're given percentages. Okay, percentages would be out of 100%. These are the different percentages that you have. And so, for example, we have 78.9% platinum, and then 9.72% carbon, and then nitrogen is 11.3% nitrogen. Okay? So, what they're saying is to do something like this, you assume every percent's a gram. And if you do that, that's like a 100-gram sample. So we're going to say, hey, this is a 100-gram sample. If we know it's 100 gram, we know the percentages match up with the grams for each one. So then, anytime you want to find a formula and their mole ratio, you got to convert all of them to moles. So the first one we would take, make it grams of platinum. We can do that one. We can take the 9.72 grams of carbon, and then we can do 11.3 grams of nitrogen. So platinum, you go through, figure its moles, like we did yesterday. Grams of carbon, figure its moles. Grams of nitrogen, so you just go through and plug those in, 195.08. Grams of platinum is 1 mole. Carbon's 12.01 grams. Carbon, 1 mole. And then 14.01 grams of nitrogen, 1 mole. So what you'll do is you'll get out some moles with decimals. I think this is would be 0.404 moles of platinum. This would be 0.809 moles of carbon. And the last one would be 0.807 moles of nitrogen. So at that point, those are just ratios, and to get them to come out to be whole numbers, or hopefully get them to come out with numbers you can compare, you would just go ahead and get them all the whole numbers, or try to get them to where you got relationships with whole numbers involved. You divide by the smallest. As you can see, this is going to be a 1 to 2 to 1 ratio, or 1 to 2 to 2 ratio. So we get 1 platinum, we get 2 carbons, we get 2 nitrogens. So then, if you wrote the formula, you always calculate the empirical formula in all of these. So all of these, you come up with the empirical formula. You'll never come. I shouldn't say you never come up with the molecular, but you know 100% for sure that the formula you have is going to be empirical. Because the empirical is the simplest ratio. This only gives you the simplest ratio. Okay? And so you would plug that in and you go, metals usually go first, so if you're assuming this is probably something ionic because it's got a metal, right? And it's got some non-metals in it. So we'll put the metal first. So it would be PT. And then we go C2, N2. Now, do you guys the second one's probably going to be on the polyatomic ion chart, maybe, if it's there. So do you guys have your polyatomic ion sheet? Do we have C2N2 there? Is that present anywhere? I don't think you find it, right?
No.
But you do have one that's a smaller ratio. CN. It's cyanide, right?
Yeah.
So you probably, to write that correctly, you'd probably go, okay, that's probably cyanide, or platinum's a +2 charge. So then it would probably be better to write it as PTCN in parentheses. Okay? Because that all that does is it gives you the ratios of all the elements, and then sometimes you have to. This would be a better formula, okay? And then you could explain that real easy than this one. Okay? Not saying this one's wrong, but when we take a look at an empirical formula, that's what you'd end up with. Okay? Now, not to take this too quick, but sometimes when you do something, you will be asked for a molecular formula. So what I'm going to do is I'm going to give you percentages, okay? And then I'm going to give you the moles. I'm not going to do this work here. I think everybody can do this work. All right? So what I'm going to do is I'm going to give you the moles at the end, and then we'll take it from there. So for the next one, we'll say we have 51.4% carbon, 8.6% hydrogen, and then 40% nitrogen. All right? So I'm going to go through and say, hey, we take 51.4, change it to grams. Now we got divide by 12, hydrogen divide by 1, nitrogen divide by 14. And when we do that, you're going to get moles out. When you do that, so that you can look at those and make comparisons. So 51.4 divided by 12 gives you moles 4.28 carbon, and then that's pretty much 8.6 moles of hydrogen. Might be a little less than that, and then this one's 2.86. So the smallest number of moles is nitrogen. Okay, and then so we know this is 1 nitrogen. We know that that is, let's go ahead and do that. That's 3. That's 1.5. All right, so now what do we need to do from there? Right, and you could just realize if you got 1.5, you could, that 0.5, you would realize you'd have to multiply that by 2. So we do each one by 2, and we get, again, the empirical formula. And so that would be C3H6N2. Okay. Now, I'm going to give you some more information. I'm going to say that the correct molecular mass of this molecule, so the molecular mass of this particular molecule with this ratio is equal to 140 grams per mole. So that ratio is did I have something wrong there? Okay, never mind. I was thinking something else. Okay, so what do we have to do to see if they match up? Just find the molecular mass of this, right? Like we did yesterday. So this is 36 for carbon, hydrogen 6, nitrogen's 28. Add them up, 12, 20, 2, 5, 70. So 70 grams per mole. Everybody knows what I did, right?
Yeah.
Took 3 carbons, 20, 36. 6. So then what's the actual formula going to be? Yeah. So actually we got to multiply everything by 2. And then we got C6H12 in 4. And that's how it goes together. So you have 6 carbons with hydrogens hooked off and nitrogens. But really don't know the structure of it. As you know, molecules, they can be really lengthy and big structures with lots of carbon and hydrogens hooked off of them. But this would be what we call the molecular formula for that. So I went through that really quick. And so anytime you want to find empirical formula, you've got to find moles of everything. Once you find moles of everything, you just go ahead and try to isolate it down to simplest whole numbers, which we know atoms go together in whole numbers. So we try to do that. And then if something is not a whole number and it's a half or a third, we're going to have to multiply by the reciprocal of that to get those out all to be whole numbers. And if something goes wrong where you can't get it and you start getting these huge numbers that you have to multiply by, then you did something wrong probably in the process. Okay? Any questions you have on that? So that's empirical and molecular, and that was part of your assignment that you were doing. There's some other things like on isotopes that you're asked questions on. Isotopes would be where you have, they're used to determine average mass. So all these masses up here are averages. So everything you see up here is an average. Okay? Except, we were talking about yesterday, I think there's maybe one, or there might be more than one, where there's only one atom for it. Okay? So all of those are, all these masses that we're using for their molar mass, they're all averages. Okay? Because you're taking out trillions of atoms. And you're going to get so many of one isotope and so many of the other. I think you have like, one of the questions you had copper 63. I believe it's 63 and copper 65. Is that right? You had a question like that. And copper is 29. And the and copper's average atomic mass, or its molar mass, is 63.546. And so the question was asking you, which one has a higher percentage? Do we have a higher percentage of copper 63 or copper 65? 63. Right. So 63 because our average is closer to this. Because most of the weights are going to be pretty close to 63. They're not exactly 63. So, but most of the weights will be close to your whole number for your protons and neutrons. So it might be like 62.99635, something like that. And this one could be 64.99732. But you can kind of tell that this one you have a higher percentage of this one. So if we knew the percentages of them, then we can figure the average. Okay? So if I knew the percentage of this one, all I'd have to do is take the decimal form of the percent and multiply it by its mass for both of them. and then add them up at the end. We had some students struggle with that a little bit, so I'm going to use this as an example to see if I can come up with 63.546. So I'm going to get the data for copper 63 and 65, and then I'll be done. Okay, and then you can ask questions, work on things, whatever you need to do. So let me look that up real quick because I have that in this book. If you guys have any questions, why don't you go ahead and get your homework out now. That way, if you got some questions on certain things that you came across as a group, you think it would benefit us as a group to visit about it and talk about it, we sure can. If not, then you can continue to work on those ones that we didn't do some empirical with. Okay, so copper 63, this one here. So if we have what's called copper 63 in I heard you guys talking about biology. Biology likes isotopes written like this. This is what biologists like. They don't want to get too complicated. Okay? Don't want to go over their heads, biologists. Okay? Got to keep things down at a level they can get. All right? Don't tell the other teachers I said that. Okay? So this one here, I'm going to go ahead and erase some of my work up above. So copper 63 percentage-wise in nature. Now they have what we call a mass spectrometer. And a mass spectrometer basically sends these atoms. They get them into a vapor, and they send these atoms through these tubes. And then, as it goes through the tube, these atoms are deflected because of their nucleus. They're charged. The nucleus is charged positive. So then they're deflected. The one with the bigger mass has the bigger momentum, right? Bigger momentum travels farther. They're less likely to be deflected. The lighter one travels not as far. And then they can figure out how many they hit in a certain area, and they can determine percentages based upon how many hits they have of 63 and 65. So the percentages for copper 63 and 65, 63 would be 69.15% of the time. That's copper 63. And of course the other one has to make up the rest. Okay? So that would be 30.85%. Okay? They find out their masses too, based upon protons and neutrons. And 63, 62.929 AMU, we call it. So this is the percent, and this is the mass in AMU, atomic mass. And so then this one is 63 point, or 64.928. So at this point in time, when you have this information here, and what you can do is you can take the decimal form of the percent and multiply it by 62.929. So basically we take this 0.6915 and we multiply it by its weight, which is 62.929. And that gives us an answer, and then we'll do the same for the next one, 0.3085 times 64.928. when we do that, we're going to add those two together because that gives us 100% of the weight. 0.6915 times 62.929 gives us 43.515. So you can see it makes up most of the weight. The other one's about a third of that. But it's a little heavier. And that gives us 20.030. And so then we get an answer that's 63.545. So I think that's, is that it? 546. So we're off a little bit. We're close. There's a question on there also. If we have a sample of copper, how many times are we going to be able to pull out a copper that has this atomic weight? None. Zero. Zero, zero, zero. So anytime you have isotopes, you'll never have an atom that has the weight that's on the periodic table. That's the averages. Okay. All right. Any questions you guys have come across that, as a group, you think maybe we could go through? Well, I'm going to give you guys the rest of the time to use your knowledge to, I think you guys got about 10 minutes or so, or a little bit more.